All right, we're gonna get started soon. Yes. Grab a beer if you still haven't grabbed one in the fridge over there. All right. So I'm Johan. I work at Stylight as a tech evangelist, and I created this meetup like a month ago, and I'm like really impressed by how many of you showed up today. The first meetup I created when I arrived in Munich was like a Docker meetup, and we were like 20 people. But like, yeah, I think we are more than 100 now. Like 160 on the meetup group. That's pretty amazing. So tonight we'll have Adam talking about neural network. He will introduce himself, and then we will have Fausto talking about deep learning and application in computer vision. What else? We also do some machine learning at Stylight. If you want to know more about that, we have some people in the room over there. Or just reach out to me and I will connect you. All right, Adam, are you ready?
Hey everyone, my name is Adam. I have some experience with machine learning, but not a lot. Working I got it working at IBM, Samsung, and then Bloomberg on stuff like computer vision and fraud detection in financial transactions. Today I'd like to introduce you to neural networks. Well, neural networks are hot today, or at least they appear to be. So they make news, they appear on the covers of popular magazines, and well, everybody just seems to love them. Is this justified? Did neural networks bring about any real change? Do they do anything better than other approaches? Well, I'll try to convince you that in fact, yes. Neural networks are, well, maybe not superior, but they add up a lot to your toolbox as a machine learning engineer, and they can, well, revolutionize your work and improve your results quite a lot. So what's hot about neural networks? Well, what they bring to the table is, in my opinion, unparalleled descriptive power. Well, they learned feature representations that are simply impossible to design by hand, and they vastly outperform almost anything created before. Unsupervised learning, so not only they learn features, but they can do so without you telling them explicitly what good really means. And unsupervised learning isn't anything new, but here you can use it to train a network and then to transfer that knowledge or for your supervised training problem, which wasn't that easy before. And whatever your problem is, you might be able to benefit from this unsupervised pre-training, let's say. There are also vast modeling capabilities hard to find in any other machine learning algorithm. You can work with text, with audio, with images at the same time, And of course, you can do that with any other machine learning algorithm, but then you have to extract those features and merge them somehow. While when using neural networks, you can do that at the same time using only neural networks to extract those features. How about learning time series or sequences, especially without data dependencies of undefined length between the data samples? Well, you can do that. Or maybe learn data generating distribution and samples from it. Well, there's a neural network for that as well. But that's just me talking. Let's have a look at a few examples of why I think neural networks are cool. So how do you handle time-dependent data? If you care about numbers, you can use stuff like auto-regressive models or maybe moving averages. Or in natural language processing, you can use n-grams, which model temporal dependencies as well. But what if you wanted to answer a question like this one based on the input of these 4 sentences? Well, in this example, you might think it's simple. The question is about John. You just pick the last sentence where John was mentioned, and you try to infer the answer. And the answer, of course, is bathroom. So let's move to a slightly more difficult example. Here, in order to answer that question, you have to learn a concept of a lion. Well, if you learn that concept, the question also becomes easy, right? Because then you know that a Brian is a lion and it's white. So how do you go about learning a problem like this? You can come up with some complex knowledge representation based with a system that infers new facts and proves them. But how about doing that with a single algorithm in which you just feed in a sequence of sentences and an expected answer? And that's exactly how an end-to-end memory networks are trained. These networks use a recurrent attention mechanism and an explicit memory bank to kind of learn how to address that memory, what to write there, what to read from it, and how. The beauty of this approach is that it's trained just like any other neural network by using a backprop, which we'll also look at today. So slightly different example, describing images. So we as humans have no problems at all with describing images, do we? Well, I'd say that's partly because we have excellent hardware that's designed exactly to do just that, and partly because, well, we have years of experience. But again, how do you do that with traditional machine learning? Well, when you think about how you describe pictures like this yourself, you may start with object detection, and maybe wonder what type of a scene that is. You can recognize activities and pick some reasonable candidates based on the context. You can then develop an intuitive understanding of what's going on. And finally, using your communication skills, like language proficiency, you can just write down the description. Each of these tasks is incredibly complex for computers, and there's no final solution for them. And yet you'd have to handle uncertainty of all these steps and kind of combine them together. Well, it appears you can go about the problem a little bit differently. You can encode each of these images using convolutional neural networks into a vector representation, and then you can use a recurrent neural network to create a sequence of words or a sentence to describe it. There's only a little problem with this approach. This vector representation of an image would be a global descriptor, and that means that you lose a lot of information on which you could base your descriptions. As a human, when you describe an image, you rarely look at the whole of it. You just take a quick glance to infer some contextual information, and then you look at different objects. How about doing that with a neural network? Well, it appears that these descriptions were generated like that. So again, recurrent neural network is trained to look at different parts of the image. These blacked out images show at which part of the image a network was focused while generating the underlined word. The network decides itself when to end such a description, and these are the resulting descriptions. Well, I'd say it's pretty amazing. Well, there's yet another example. So combining high-dimensional sensory input to aid control is yet another feat of intelligence we couldn't figure out how to replicate. Well, or until recently, Google's DeepMind seems to have figured it out. So this model uses raw pixels as input and the score to learn to control this pad, and to play the backgammon Atari game. After around 10 minutes of learning, it's not performing very good. It can barely hit the ball, and I'm sure that almost anyone in this room could outperform it on our first try. But what happens after 2 hours? It achieves the level of a human expert, and we would barely stand a chance against it. But that's not all. In a second, we'll see what happens after about 4 hours of training. Well, after 4 hours, it uncovers a new strategy that was unknown to human players before. It digs a tunnel on the one side because it figures out that's the fastest way to win this game. Pretty amazing, isn't it? And that's all without the knowledge of what actions it had. So it could move the pad to the left, to the right, or stand still. And it had to pick one action at every time step, but it had no idea what these actions will do. And it had to figure it out itself. Okay, so we've seen how cool neural networks can be. Let's now talk about why is it that they're so good. Is there anything special about neural networks, better than other machine learning algorithms? So before talking about why neural networks are so good, let's talk about why machine learning is so hard in general. So what we're fighting against most of the time is the curse of dimensionality. And I'm sure that every one of you has heard about it, but let me reiterate. So if you take a distance in 1D and divide it into, say, 4 regions, you don't need a lot of points to represent it. But what happens if you move into 2D? The number of regions grows to 16 and to 64 in 3D. So in general, the number of regions grows exponentially with the number of dimensions. Now suppose you wanted to fit a k-nearest neighbor classifier to classify some data. Well, the exponential growth of the volume makes the distance between your nearest points grow exponentially as well, and that makes your problem especially hard, because while the distance between points grows, your classification might become just meaningless. Well, in reality, however, the number of variations of your problem is different from the underlying dimensionality of your data. And we can safely assume that the data sits on some, well, lower dimensionality, on some manifold of lower dimensionality. So we designed features to kind of, try to get our original input space to that manifold, in the hope that it will be easier to manipulate and maybe guide learning. But the truth is that we don't really know what makes good features, and when we design them, it is disjoint from the learning process itself. So features we design are usually high dimensional and verbose by themselves anyway. Another problem is that a lot of our learning algorithms rely on the proximity of the points in the input space. So the k nearest neighbors is the simplest example, but even if you take an SVM, well, it uses super vectors to represent the decision boundary. And when the number of dimensions gets bigger, the boundary gets more and more complicated, and you need more and more points to represent it. Well, and it doesn't get any better. So you see where it's going. We need a lot of points, and that just means very poor generalization. Can we do better? Well, the answer again is yes. We can introduce priors to our model. One such prior would be to assume that our data is probable and representative. Why is it a good prior? Well, if you look about image and the probability of getting that image from, for example, a uniform random distribution, it's really low. So the probability of getting a pixel of any color is like 6 times 10 to minus 8, and then you have to raise it to power equal to the number of pixels, and that's the probability of getting this color. But another prior, perhaps more important when it comes to neural network, is that, well, visual data can be represented hierarchically. Well, if you reason about the world, that's how we think about it, right? We don't think about, I don't know, a chair in terms of parts from which it's built, but we think about the concept. And just maybe a deep representation, a hierarchical one, might be better suited to represent the world than a shallow representation. So again, typically in machine learning, we project our input space into some feature space that is supposed to aid our learning. A curious thing is that the learning algorithms we use are really very simple. The final models becomes huge and very complicated, but not the learning algorithms themselves. And what's really complicated is just the feature extraction. For example, here we see a bag of words approach to object classification in computer vision. So what you want to do is to encode an image as a histogram of visual words, and then you can, for example, classify it. Typically, the first step of this approach is key point extraction. And for that, you might use, for example, the well-known SIFT algorithm. Another curious thing, its author, David Lowe, claims it took him about 10 years to figure it out. And yet it's only one step of this approach. By the way, this paper about SIFT is the single most cited paper in computer vision, and that's just tells you how important feature extraction is. So typically, it might take anywhere from 6 months to 2 years for a team of engineers to design a good feature representation for a problem, well, if it's new. So there are two natural questions. Why are good feature representations that important? Well, we've partially covered it. The second one would be, is there a way to learn these features? Well, there is, and that's exactly what neural networks do. Here you see filters extracted from a neural network for face detection. And it not only learned feature representation, but it did so in a hierarchical manner by composing low-level features through an intermediate level into high-level features. So here the first layer learned to detect edges and some blobs. The second layer detects parts of a face, and the third layer detects full faces. Let's look at slightly different examples. That's taken from a neural network trained to classify objects into one of the 1,000 categories of the biggest computer vision dataset out there, ImageNet. So on the left-hand side you see filters, and on the right-hand side you see those filters mapped into input space. So basically image pixels. Maybe that's not too important for the first layer, but we'll look at the further layers in a second. And there it's not that easy to judge what a feature is about or a filter is about just by looking at it. So here again, first layer, some blobs, colorful these times, and edges. In the second layer, well, we have some more complicated patterns, like corners, different textures. By the third layer, we get object parts, just like in the face detection neural network. You get some car wheels, like here, and pumpkins and other round orange objects here. You also get a human detector. What happens later? So in the layer 5, there's something really interesting going on. The network managed to learn fully blown object detectors, and that's something more. These objects vary a lot, not only in appearance, but also in scale, shape, or orientation. Until this paper appeared, we really did not know that that neural networks can be rotation invariant, for example. So there are features that can indicate a presence of a flower or of a dog. And it's not like there's a human that really explicitly made this model invariant to anything. This is all inferred from the data. A little sad fact is that we don't really know why it happens. We only know that it does happen. Well, it's a consequence of minimizing an error function, which is really how we train a network. We know how the optimization works, but we don't really know what causes the invariance. So we've seen some cool neural networks application, and we've peeked into the regions of representations learned by neural networks. Let's now have a look at what neural networks are and how do we train them. So it's an introductory talk, so let's start with very basics. And I'm sure every one of you has heard at some point about linear regression, but I'm not sure that you know how a neural network works. So let's explain a neural network in terms of linear regression. So if you take an input vector, x, and you feed it through a linear regression, a multivariate one, you get an output vector, y. So having a training set, you can then assume Gaussian errors on the outputs, and you can maximize the log likelihood, which corresponds to finding the least square fit of your data. So then you could also chain multiple linear regressions and achieve a deep representation. Only it wouldn't really work. Well, chaining several linear transformation is still linear transformation, a different one, but still linear, and it doesn't really add up anything. To get any benefits, you would have to add some kind of nonlinearity between those stages. Secondly, linear regression is a supervised model. So if you wanted to chain them, you would need to get the intermediate targets from somewhere. And well, you just don't have them because you don't know how to build a hierarchical representation here. So a neural network is precisely this multi-stage or multi-step linear regression with nonlinear functions inserted between the stages. Only you don't need intermediate targets because they're figured out automatically to minimize the overall cost function. Or if you want, you can think about it that the intermediate targets are chosen so that at one layer, so that the prediction on the next layer has the lowest error possible. So once you have an idea of an architecture you want to use, you need an appropriate cost function which, well, you minimize. And that's how you do the learning in a neural network. So speaking of the architecture, you can add some more layers. Why not? And before long, you get a deep architecture. And what does deep even mean? So a network being deep is really data dependent. So for some applications, 2 or 3 layers might be deep enough. Maybe there's nothing more to gain. In other applications like computer vision, you can go like 15 or 20 layers. One of the recent winners of the ImageNet challenge, which I've mentioned, had around 150 layers, and that's really what delivered the discriminative power needed on such a huge data set. From a high-level perspective, a neural network is just a computational graph. So you can have inputs to different layers, you can have outputs from different layers, you can have also bidirectional connections. So here we see just a feed-forward model where you input something at the beginning and you just forward propagate it, but it doesn't have to look like that. Convolutional neural network is an extremely important type of a model, especially in computer vision. So let's start with a simple convolution. You can take a rectangular filter of weights and just slide it along the input. So at each location, you just multiply the weights with the inputs that overlap with the weights. You just sum this up and you store that at the location corresponding to the center of the filter. And that's more or less how convolution works. We can extend it to a convolutional layer. How does that work? Well, you have several input maps and several output maps. So at the beginning, if you have like a color image which has red, green, and blue channels, that means you have three feature maps. And then for every output map, you have as many filters as many input maps are there. You take each of the input maps and convolve it with one of the filters, and finally you sum up all the responses to get an output feature map. That's only one convolution layer. If you stack a couple of these, you get, well, guess what? A convolutional neural network. Convolution is not everything that's happening in such a network. There's quite some more. So between the convolutional layers, you get some subsampling layers, which subsampling really means aggregating values over some windows to reduce the dimensionality of the data. Today, the most commonly used subsampling is the max pooling, which just takes the maximum value, and it gives you a lot, maybe not a lot, but some invariance to translations of pixels. What you also have is, or are nonlinearities, usually after the subsampling layer, and also at the end of such a network, you get fully connected layers, which are just the old-fashioned multi-layer perceptron, which here really acts as a classifier on features extracted by the convolutional part of your network. In fact, you can cut out this layer once the network is trained and use your favorite learning algorithm, for example, SVM or maybe bagging or random forest, to use that features and to solve your machine learning problem. By the way, both so two of the three examples we've seen at the beginning, the Atari player and the caption generating framework used some part of a convolutional network to extract features. So yet another class of models is a recurrent neural network. It's recurrent because the state of the network depends not only on the input but also on the previous states of this network. And different from like vanilla perceptrons and convolutional neural networks, neurons of this particular type of network can also have hidden state, here denoted by H. So when a new input comes in, it's sort of concatenated with the old state to form like an augmented input, and that's fed in further. So the output really depends on the state of the network. What this network is good for? Well, it can model temporal dependencies and it can also model sequential data. So from today's example, the caption generation and the question answering network used this approach. Also, you can merge several different architectures, for example, so we can easily create, recurrent convolutional neural network if that's what you need. So training a neural networks really boils down to minimization of an error function. So normally you use an iterative minimization procedure, an error given as a sum of errors over the training samples. So choosing an error function is a part of the modeling process. So it really depends on the type of the question you would like to answer. Well, once you have it, you want to train the network as long as an error on a validation set decreases. And having a validation set here is really essential because neural networks are really powerful models that tend to overfit. So if you do not have a validation set or a test set and you just test its performance on the same data you train on, you can get whatever accuracy close to 100%, but it's not very meaningful. Modern neural networks have several millions of parameters to learn, so that means that you should use as much data as possible. But if you don't have that data, well, don't freak out. There's a way around it. You can use unsupervised pre-training, for example, or you can train a network on a totally different problem, and then just use a very tiny data set with as few samples as several per category to fit this network to your problem at hand. Back at Samsung, we've done a little experiment. So the neural networks from the ImageNet were something very new and quite hot, and we wanted to see how the features extracted by this network perform of different kind of data. So we decided to do speaker recognition with audio using a network trained on visual data. Do you know what? It worked like a charm. You really can use a network from a different problem for something else, especially if you don't have data for it. Well, but it would be good if the problem the network was trained on was close to what you're looking to solve. So again, error functions are a modeling assumption, and then if you want to do regression, you will be good with the mean squared error, which assumes Gaussian errors. If you want to do classification, you might be good with the cross entropy, which is just maximizing data likelihood under categorical distribution. And something quite recent is the similarity ranking. So here you want to rank your samples from a data set based on similarity. So what you want to do is learn a distance measure. This distance should be maximized for samples that are different from each other and minimized for samples that are similar to each other, with the G being a constant that regularizes that gap. And this error function is a hinge loss variation for that problem. So typically, when you want to use a neural network to solve a particular problem, you don't have to design new error functions. Only if you have some really non-standard problem, you have to fiddle with it. And that's really where the fun begins. So what about minimization? What you basically do is you follow the gradient. So if you take a gradient of a multivariate function, you get a direction of the steepest ascent. So that means the direction in which the function rises or grows the fastest. If you take a negative of that, you get a direction of the steepest descent, which you can follow to minimize your function. Of course, you have to evaluate the gradient every now and then to kind of confirm or to find a new direction. And that's more or less how stochastic gradient descent, or SGD, works. That's by far the most popular minimization approach for neural networks. So what is it? Well, instead of computing the gradient on the whole data set, it samples a batch of some fixed size, a lot smaller than the whole data set, and it computes the gradient on this batch. And then it updates the weights based on that gradient. So it has one disadvantage. The gradient you compute is not as accurate as it would have been have you computed it on the whole data set. But there are two huge advantages to it. The first one is that it's way faster. So especially if you have like a large data set, you can, with this approach, perform thousands of updates instead of just one. It also brings in some stochasticity in your process, and that helps you to not get stuck in local minima. Also, stochastic gradient descent is very sensitive to step size. Here, that's the alpha. If you set it too low, your optimization will just take ages. If you set it too high, it will stall or diverge. You have to, just choose it empirically, and once your training starts to converge, you probably should decrease it a little. You can also use some adaptive approaches that help you choose the step size. That would be, for example, AdaGrad or RMS prop. They not only choose an adaptive learning rate alpha, but also sometimes, or depending on the algorithm, they can choose different learning rate for every weight of your network, which significantly speeds up the convergence. So I'm also sure that you've heard a lot about backpropagation. So where does it come in? Well, maybe a big news, backpropagation is really not a learning algorithm. What backpropagation is just an efficient means of computing gradient on a computational graph, and the neural network just happens to be a computational graph. Why is it efficient? Well, its complexity is O(n), where n would be the number of weights. A different approach to computing gradients by, for example, finite differences would take you O(n) squared, which is, well, when you have millions and millions of parameters, that would take significantly more time. So backpropagation is just an application of a chain rule on a composite function. So here, if you want to compute the derivative of z with respect to x, or maybe let's talk about the flow graph a little. So here is a flow graph. Say x is your input, you multiply by weight wxy, you plug it into y, and then you apply some kind of nonlinear function. Then you multiply y by wyz, feed it into z, where you also apply some kind of a nonlinear function. And then you want to compute a derivative of the output z with respect to x. So if you just apply the chain rule, these derivatives would be derivative of z with respect to y times the derivative of y with respect to x. And that's how backpropagation works. So where does the name come from? Well, so first you have to do the forward propagation to kind of compute the outputs of the network, and then you would like to backpropagate it by computing derivatives at every stage. So that's where the name comes from. And there's also a similar approach to approximating the second derivative, which could potentially speed up convergence, but it doesn't work too well with mini batches, and that's why it's not so often used. Well, I'm going a little bit faster than expected, but that's not bad, I suppose. So we're coming to the end of the talk, let's summarize. So we've learned why neural networks are cool. In particular, you've seen how to generate image captions and play games with a neural network. You also know what networks are and why they can be better than some other machine learning approaches. Finally, you know a little bit, at least in a simple case, how to design a neural network and how to train it. Well, I hope I've managed to convince you to give neural networks a try if you use machine learning. And for that, well, I have a simple request. Just try them out. So at the beginning, it might or it can take a while to get everything right. But once you do that, once you get to use neural network, you'll see that it might improve your results a lot. So to help you a little bit, here are a couple of tools that you can use for using neural networks. So the first one, Fiano, that's in Python. It's quite easy to use as most of the tools in Python. And yet it's extremely efficient because, well, it compiles your neural network or a computational graph in general before running it. The second one, Caffe, well, I of course recommend it, but that's because I'm a contributor. The truth might be it's a little bit stiff for today's standards. So if you start with something today, you might be better off with one of the other tools, but it's still probably the most efficient, and therefore might be worth giving a try. So TensorFlow is a new tool from Google. It's not as good as it's supposed to be yet, but the Google guys are working very hard from it, so it might become really good pretty soon. And there's Torch. It's in Lua programming language. It's extensively used by Facebook, and it's supposedly very easy to use. Well, I haven't tried, but probably. And if you wanted to go deeper, here are some additional resources. So that would be it. Thanks for attention, and well, I'm open to questions.
Yeah, I got a question related to image processing. Would you think a network can learn how good a picture is? Say you have a given number of photos, say 1,000, you have a rating, how good that, or some person liked that picture. Can a network then for a random picture without the rating, like guess how nice that picture might be? So it's not characteristics you can directly find, probably like blurriness or whatever, but like meta characters or so.
It's a good question, and there is a model that I believe does something similar. So some guys from Stanford developed a model that judges how good your selfie is. They downloaded really loads of pictures from Facebook, and based on the number of likes a picture gets, they will just judge how good your selfie is. So I suppose that's more or less what you're asking about, and if they could do that, I suppose you can as well.
Yeah, well, if you have faces, I guess, I don't know, maybe that might be easier, but if you have, like, yeah, say you are a hobby photographer, you take pictures of just everything. That could be nature, could be people, could be whatever. Would you think that's possible to distinguish some characteristics, like the color, form of color, is it whatever, or, I don't know.
No, one thing to look at would be the composition of the image, and there are some ways to judge composition, like a composition of an image, or composition of an image can be thought of as good or bad, and if you take that into account, it might be possible to learn something like that. But I think that for such a problem, you would need a supervised learning set, maybe quite a big one, and the question is, where would you get that from? Once you have it, you can, of course, try to learn it, but I cannot guarantee it will work. Mm-hmm. But you would have to need that training set. Maybe you can use like pictures from Flickr for that with likes and similar stuff.
Yeah.
I'm not sure.
Thanks.
Hi, thanks for your nice talk. I'm very curious about your remarks on generalizing or reusing networks that were trained in one situation with one kind of data and then use them in another situation. Why should this work? Why did it work in your case? And is there a more general theory on this?
So the whole thing is called transfer learning. I cannot really speak about transferring features between totally unrelated problems like visual and audio. But if you have, for example, computer vision challenges, well, if you think about our visual system, it's when you look at something, you have only one pair of eyes that processes it. And then you have a lot of different systems in your brain that uses this representation to do whatever is necessary, right? So it might give you a hint that maybe there's only one good representation, or maybe several of them, but they might be pretty similar for example, visual data. And that means that when you extract features from images, they will be pretty much the same, whatever your task is, at least the low-level features. And then so following that can give you some intuition why it might work.
Yeah, but I think the great difference is you use if you use visual data, I think I can get the concept that there are underlying higher features that can be useful for many tasks. But now you have visual data and you have audio data, which is very, very different. So that this still works just amazed me.
Well, I don't know for sure. I can only suppose what's happening, and the only thing that comes to mind is that both audio and visual data are signals. If there is some patterns within that signals, you probably can extract it. Is there any similarity? I have no idea. I only know that in this particular example it worked, and well, I can send you a paper about it if you write me an email.
So you listed a couple of packages that one can use to do deep learning or learning with neural nets. Could you give us an idea of when to use Piano versus when to use Caffe or whatever? Like what is where does each package shine? When should I use that package? But, yeah.
Okay, so let's limit the scope a little bit. I haven't used TensorFlow or Torch, so I can't really talk about them. As for Piano and Caffe, Piano seems to be more flexible and easier to use in research because you can accomplish a lot of stuff coding in Python only. But then it has a pretty low-level interface in terms of like matrix multiplications, and you have to build on top of that for example, a layer or a neural networks. So these things aren't there. You have to build them yourself. But once you have that, it's pretty flexible because if you want to try a new model, you can just code a new kind of layer in Python, and that just works. As for Caffe, well, it has a pretty good interface in Python, but you have to do a lot of coding in C++. And for example, in Piano, if you code your new layer in Python, you can just run it on a GPU. In Caffe, you have to code that in C++, and if you want to run that on GPU, you also have to code it in CUDA, which slows down the process a lot. But then if you want to take it in production, you will be far better with Caffe because Piano has to compile everything before starting it. So that means that every time you for example, power off your workstation, power it on again, you would have to compile it again. So depends. Research, piano is better. Production, I'd go with cafe. And I thank for your attention.
Thank you, Adam. All right, so we'll take a little break, like 10 minutes, and then we will have Fausto. We will have a TensorFlow meetup on March 1st here. So for those interested, just check it out on meetup.com. Yep.
What did you do anyway? Did you really take the fixed network and just edit top layers? Or did you allow all the weights again to change when you started training?
Typically, when you have cut out the fully connected layers, but usually you leave the convolution part intact. Depending on the implementation, it might be a little bit problematic because of the different input.
Yes, because you have usually, I mean, an image is two-dimensional, and now you have audio, which is one-dimensional.
Yes, but the beauty is that the convolution does not particularly it just works on higher speed so to the convolution you just take a feature and you slide it to right?
Yes, but it also has a two-dimensional spatial structure, right?
Yes. Well, I'm not sure if about this particular example because it was technically done that it was a colleague. What I suppose you can do is you can like just copy the wave, the audio wave, and just treat it as an image in that sense. But yeah, but this colleague of mine published a paper on it, so I think it's fine.
Okay, cool. Yeah, because I think that there's a general thing which also works in biological networks. If you lose part of your brain, and this is a crucial functionality, then usually it's mapped to another part of the brain. And it's much faster than if you would start from a random state. So somehow there's something more general, but if it would be so general that you can use your neural network trained, for example, the Google image network for almost any task, this would be incredibly useful because you can save a lot of training data, a lot of training time. So how much is generation worth?
Yeah, it was a nice talk. We should talk. So you work for us?
As a Kiwi, yes.
Yeah, we should meet then. We should meet once.
So I would go to all
people have a hard time to.
Okay. Okay, works. Seems like. Yeah, works.
All right, we're gonna start again.
Okay. So, good evening. I'm Fausto Militari from the Technical University of Munich. Tonight I would like to talk to you about my most recent work about TAP-CNN, which is a segmentation method for medical images that uses convolutional neural network at its core. So, as you can see, I chose some background images that has nothing to do with medical imaging because they look very ugly. The medical images look very ugly when you expand them too much. And also because I will talk a little bit about computer vision in general, as the previous speaker did. But yeah, as an introduction again, some concept will be repeated. So computer vision is about teaching machines to see and understand the world, the information, the structured information that we have all around us. And to enable machine to see, we need to represent them in a computer system. Images are a collection of pixels, matrices that have three channels of intensity values forming colors. And recognizing complex patterns in these simple intensity is very difficult because we cannot concentrate ourselves at the level of single pixel, but we need to consider more structured information. So we need to look at bunch of pixels to recognize complex patterns, and at the same time creates models that convey our own knowledge and our own experience of the world into a computer in a structured form. So how can we describe the world, how to extract meaningful information from images, and how to build good models of the world? For example, we can extract features. Features can be used to represent the world, represent objects. In this way we can recognize buildings, we can retrieve images, we can recognize different animals, or simply tell people apart. And you can see, for example, here there are some corner features that are quite old, texture features that are used for segmentation of an animal, edge features that describe the shapes. So we had three different ages, I would say. The age of handcrafted features, where people were spending months and years to handcraft features specific for the task at hand. This is, of course, so each task has, let's say, its own difficulties, and you never want to extract all the possible information in the image. You want just to extract the information that's easy to extract, which means that it's always there. It's repeatedly can be repeatedly extracted, and that is difficult to find, to confuse taking one thing for the other. So in this sense, it's very distinctive. So feature must be repeatable, distinctive. For example, shapes can be described by edges. Different objects, since different objects having the same shape might have different colors, one could use also colors. And simple feature used for pose estimation, for image stitching, might be corners or junction between edges. Features comes with descriptor. A famous one already cited by the previous speaker were sift, surf, brief. These are descriptors that are used to match points or key points, exactly, feature, match them across images. For example, to do stitching or to do image retrieval. It's possible, for example, to do image retrieval from Google Images using SIFT feature. This is a very easy example you can find around. Then there was the age of when people started trying to do compressed sensing, autoencoding, and we have these tales of cats and brains, as I titled this slide. And this slide is about the fact that it was soon discovered, once the people tried to understand which signals form the images, which are the basic bricks that we can use and mix through linear combination or more or less linear combination of these bricks to form images. And it turns out these are very similar to the pattern that are recognized by the first visual cortex layer of the cat brains. So, for example, this you see some on the left hand you see stuff from a dictionary learning, and the other is MNIST dataset, so digits coming from an autoencoder. Of course, that's more tailored to the specific recognition task of the digits, so you can really see digits more or less arising from there. So recently, people started using deeper models, which go beyond one hidden layer. They are different from simple one hidden layer autoencoder because, for example, they have more, and they go as far as convolutional models that can be grown deeper because they have less parameters than fully connected models. These convolutional models, or a deep model in general, learn hierarchical representation of images. The information, in the first layer of the network, simple information is captured. On a higher level, despite the fact that you keep the filter size exactly, you can keep it exactly the same from the first layer to the last layer in terms of convolutional mask, you will discover that the filter of the last layer are recognizing a complex pattern in their receptive field that may appear in the receptive field. Convolution, there are many of these convolutional layers, for example, that can be followed by fully connected layers, and then layers that output classification labels, for example, or they can be followed, they can be also fully convolutional, having a network that is just composed by convolution and produce, for example, segmentation maps. This is exactly the same image, more compressed maybe than the previous speaker showed, where the response of the filter is mapped back to the input space, and you can see which kind of pattern was captured by that layer in the input space, in the receptive field of those filters. Okay, in deep learning convolutional neural networks, raw images are fed to the network, and this means that there must be a considerable amount of data that must be used for training, because features needs to be discovered, and you have to show variability, the variability that you want to address in your task, your recognition task. And different features may arise in the moment that you want to do classification, regression, segmentation, or the task that you want to do. Here, for example, you can see a fully convolutional network on the side, and then here you have very classical classification, the very classical network used for classification, for example, of digits there, letters there, and images in the upper row. So, through convolutional neural networks, we can address tasks that were previously impossible to address in terms of recognition capabilities, because there is no human anymore that must handcraft feature, and all the information that is really necessary can be finally used, because the importance of each piece of information, of each pattern of the image, it's decided when you learn the filters, when you learn the network. So it's not that you neglect some part of the image or some aspect of the patterns you want to recognize just because you decided like this during feature handcrafting. Of course, there are drawbacks. For example, the training data that is required is very high, and there is always a high investment in processing power to learn them. But when you have a nice GPU, you can easily address the challenge, unless you want to build huge models. Most importantly, it turned out that the output of fully connected layers, of the last layers of the network that for classification are normally fully connected, they can be used to get a very high level representation of the object of interest. And most importantly, when you plot data of different class with a different color using this feature of the last fully connected layer, you will find them very well separated, which means that the network is creating kind of cluster of data having different class. Of course, you need to embed this in a dimension that you can look at, like 3 dimension. You cannot use 4,000 dimension or things like this. So let's go now for let's talk now about deep learning and medical image analysis and about our work about segmenting brains with a voting-based strategy. Medical image analysis is quite different because the nature of the problem is very different from the normal computer vision challenges. In the normal computer vision challenges, we have high resolution images that are rarely affected by artifacts like defects of the sensor, you know. But they might be occluded, and the object may have difficult appearance, difficult to capture. They might have strange poses, and of course they can have very complex appearance, and they can occur at every orientation, let's say, every scale. In medical images, we have much lower resolution, many sensor artifacts, and object poses that are always roughly the same, and no occlusion at all, but the data, for example, ultrasound data, is difficult to interpret even for human. For example, in the midbrain that you see depicted there in the ultrasound image, it is not that obvious to understand in some of the frame which structure is of our interest and which one is not. And by the way, I cannot use the pointer. It's this one that we want to find. But this could be similar to those, or those could be. I mean, yeah, it's kind of challenging. Okay. Okay, the ground truth, yes, in medical imaging, ground truth must be traced by an expert. It's difficult to get good ground truth, and therefore you have just a few annotated training volumes or images, while for normal images, ground truth can be acquired even through Amazon Mechanical Turk, more collaborative things, because it's easy to discard the ground truth that was falsely traced or badly traced. So how can we cope with this problem of having limited data? And how do we cope, for example, with the fact that the dimensionality of the image is 3D normally? You have normally tomographic data. Should we do convolution in 3D? So if you consider also the channels become 4D, if you consider the batch become 5D, this is a lot of memory. Given this limitation, so lack of training data, the challenges of medical data, of exhibiting, let's say, in some places even complete absence of the signal or corruption of the signal, are CNN sufficient to solve a medical segmentation task at hand? And can we make use, for example, of the high-level feature extracted by the network when, for example, in the last layer, in the deep layer, to perform segmentation? So the interpretation of the volume in a patchwise manner in our work allows us to extract millions, thousands or millions of annotated patches from a single training volume that was globally annotated, then we get all the patches. So we restrict ourselves to use patches and create a model that is part-based. We want to reconstruct or to obtain our segmentation relying only on parts of the image. And we compare, to address this problem of the dimensionality, network operating in 2D, 2.5D, which means orthogonal cut of the volume, 3 orthogonal cut, and 3D convolutions that we implemented. And we show that half CNN is a good way or a good method to put on top of a CNN to get robust segmentations. The high-level feature produced by the CNN are used in this work at the core, at the very core of our system. And we compare a number of different architectures, CNN architecture, in order to show what model is more appropriate for which kind of image. Since we try in MRI and ultrasound, we obviously have to address different challenges. So, a voting strategy, so why it's called half CNN, maybe not all of you might be familiar with this concept of half transform or generalized half transform. Basically, each patch gets classified and is able to cast an opinion about where the object center lays, so where it is. Many people perform regression to do this task. So they have a neural network that regresses, for example, 10 offset, and for each pixel gives a prediction of where the object gives 10 prediction of where the object might be in terms of shift from the current position, the centroid of the object. While we don't do that, we use then the high-level feature, as I will show you, and all of our observation leverages the fact that many authors reported that high-level feature that arise from networks trained to do classification, they kind of cluster in feature space according to the semantic content or the similarity, visual similarity of the patches that generated them. So to do our voting strategy, during training we take the volume and we process them patch-wise through the CNN. We map each patch in feature space, and each of such mapping, since it comes from a training image, it's associated with an offset, which is a vector, 3D vector, that identifies the difference between the position of the patch and the centroid of the anatomy. When we are testing time, we process the volume in the same way, patch-wise, and we identify the neighbors of these newly classified patches, and we cast the votes that were associated with them. So more visually, here you can see it. So let's see. So this is a training image. This training image has a few patches. Of course, normally they are overlapping, but for the sake of clarity, in this case they are not. So the red one belongs to foreground, the gray one belongs to background, and each of the patches has an offset that identifies the centroid of the anatomy, in this case the midbrain. Here we restrict ourselves to 2D, but of course it's 3D. What we do is we train at CNN to do classification. We find a decision boundary through, so we just optimize the softmax loss in CAFE. And of course we accept the fact that there are some outliers. And after the CNN is trained, we extract the feature from the upper fully connected layers, and we process all the patches belonging to the foreground only through the network. Each one of these patches will occupy a certain spot in feature space where they basically, we store at that position, in correspondence of that spot, the vote, which is in yellow here, which is not the best color over white background, and the segmentation, the day coming from the ground truth, which is depicted in this kind of red transparency thing there. Votes and segmentation in feature space. So, just to be clear, the classification will come from the classification output. This is of course not our network, but it's just for the sake of showing. And the feature comes from the last fully connected At testing time, we have a bunch of non-classified patches, which are not depicted in the best colors because they're depicted in black. And we extract all of them. Of course, they are overlapping. And we obtain features and class. After a while, few seconds, the classification happened, and we have a high number of outliers, like it is normal to have in this kind of problem. In ultrasound image segmentation, image classification, patch classification is difficult. So we have these many outliers, which are in red. They were classified foreground. So some of them are correct, some of them are incorrect. Classified in red, which means foreground, and gray means background. We project them in feature space as these small round gray dots. And we start looking for k nearest neighbor in feature space of each one of these gray dots. We get back the information acquired during training in terms of votes and segmentation. So each one of those, the other side, the neighbors have votes and segmentation. Then each one of these patches that was classified correctly or erroneously as foreground is able to cast some votes, k votes at most. And of course the vote map will look a little bit messy, but the important thing is that the centroid is identified correctly, the center of the anatomy, which is there, because the most part of the vote managed to accumulate there. And that's this gives us robustness to the fact that there are many other kind of looking alike regions in the image that may be segmented with a normal method that will just segment based on intensity, based on anything. Most probably this region will be also segmented as part of the foreground, but they are not, because the region that we are looking for is just one, and sometimes half of it is not seen, cannot be seen. So we have to have this kind of robustness to missing stuff. So we found the object centroid, we discard all the votes that didn't accumulate in the object centroid, and we trace back the vote from where they were originated from, and we apply there the segmentation coming from the ground truth. So in this sense, we have an implicit shape model, because we kind of project many contributions to form a final contour, all coming from shapes that have been seen during training, that are part of the training set. Of course, if the object undergoes a large amount of deformation, it's necessary to train with all the deformation, or it's necessary to use another method. In the brain, nothing moves, or there is just a variability, it is the normal anatomical variability. We experimented our method in MRI and ultrasound. In MRI, we had 27 different regions of the deep brain acquired in iron-sensitive MRI sequences. Difficult to see. Some were very obvious actually to see. Some other were exhibiting poor contrast. In ultrasound, we had just 2 regions, foreground and background. We had 40 training volumes and 114 testing volume to show generalization. So we wanted to investigate the network performance when we had different network architectures, different data dimensionality, 2D, 2.5D, and 3D. So we natively perform convolution in 5D, because 3D plus channel plus batch. And a different amount of training data. We compared the pixel-wise classification to half CNN, which obviously perform better. So these are the 6 different networks. There's like 5 layers having 3x3x3 filters. So in case of 2D, 3x3, otherwise 3x3x3 filters. And then I think 8 layer. Yeah, 8 layer having 3x3x3 filter, 5x5, so 5 layer with 5, 7, then this 753, 9, 753. I mean, you understood what the numbers are. It's just the filter size. And each layer has 64 filters. Data dimensionality, we had this 2D, 2.5D, and 3D, which means that each patch was having that kind of structure. Now, of course, the 2.5D, the third dimension was the channels, so it gets collapsed almost immediately. And the amount of training data in ultrasound we try with 80k patches per region per volume, no, 80k patches in total, or 400,000 patches. In MRI, 135,000, 1.35 million and 13.5 million patches. The results show that in MRI, we need to look at 3D because the best results are highlighted in bold for each dimensionality and so on, for each block in bold, and then the underlined is the best of this block, the best of the best. So you see, when we look in 3D, we are systematically better, so it's necessary to do the convolution in 3D. And this is also reflected by reality, because in reality, when we annotate the training volumes, we scroll a lot in all 3 dimensions, decide the boundary, while in ultrasound, as I will show you, we just look at the axial view, and so just have one of the 3 views, depend how you oriented, how you acquired your volume. And so it's necessary always to look in 3D, and the best performing network in average is a network that is fairly simple, 753, because some regions are actually easy to see. The most part of the region and the ones that are the one that in general gets well segmented are kind of easy to see. While in the other regions that are more difficult to see, maybe a deeper network will do better. Yeah, I mean, might be. We have even the one by, so each region has its own evaluation, but I think it's not on these slides. And for example, if I have this kind of pixel-wise classification, which is very confused and you cannot see anything, after casting the votes, after tracing them back, you get this one, which is of course not the best. This is the worst network that you saw here. So it's 753, but here, this 753. With the 135k patches of training. Well, this one is, you see, when you increase the number of training patches, here you see that the pixel-wise classification is much cleaner. The half segmentation is better even than that, but slightly. So this means that our method is robust to lack of training data, to the fact that you don't have always a lot of training data, because in the 2 cases, the segmentation is fairly clean. For what concerns ultrasound, we showed that the best performing network is, even not depending on the training data anymore, a complex network. In the first case is small Alex, which is a kind of an Alex net, but simplified. And for the second one is this very deep 333, so 8 times 3. This because in ultrasound, and most importantly in 2D, the data is best segmented when you use just 2D image, because when you bring in the other dimensions, you are just bringing a lot of not useful information, because if you slice these volumes differently, you will not see anything. It's very difficult even for an expert that has not been trained from a specific view to see when you change slice. So this, for example, is the slice that used for 2D, this cut, where you see it like this. And of course, this is the most distinctive. I will never think about showing you the other 2 cuts, because I will not be able to tell you where it is. I've not been trained with those. So yeah. So in ultrasound is a bit more difficult, so this justifies a choice of a network that is a bit deeper. Yeah, thank you, that is it. I kept it short. Thank you. If you have questions, yeah. Maybe this one you need. I don't know if it works already. There is a switch. Switch? Yeah.
In ultras.
Well, occlusion, so in MRI is not a problem. In ultrasound, occlusion can be understood as lack of signal. For example, if in this kind of data, in the transcranial ultrasound data, the challenge is that you are acquiring through a bone, this bone here, and it's thin, but it shadows the signal much. So what you experience is that in some patients which have a thicker bone, you will see just half of the midbrain from one side, or you will just kind of see the other side, but not really. You see one side brighter and the other side less bright. Also because you have two strong edges or two strong interfaces where signal changes a lot, which is basically the two hemisphere, the interfaces between the two hemisphere. True that is kind of joint where it is the midbrain, but yeah. So in that case, so what we have in ultrasound occlusion in this sense, that we have shadows, we have dropout signal, so we don't see. In this sense, can be understood as occlusion. Okay, a baby it's already better, but can be shadowed much. But this is also one of the strength point of this method, because if you see, it's a method that is part based, in the sense that okay, it's part based, and this does not. So if I would systematically miss many pixels here, most probably the other pixel which are slightly above that voted still for the center, the correct center, they will get a reprojection of a segmentation mask, which is this big, let's say, like here, right? And will cover all the surrounding. And of course here, it's just for the sake of presentation that they are so small, but when we reproject portion of the midbrain, we reproject a good quarter of it. So it's already each one of this single contribution, it's 1/4 of it. And we have millions of them, or hundreds of them, which kind of average. They get averaged, they create a confidence map.
Okay, thank you.
Yeah, welcome.
More questions?
Yeah. Microphone comes.
Thanks.
Final slide, this one.
Yes. You say, okay, the deepest one performs the best.
Yeah.
And I don't know, if you just compare it, for example, to the top one, this is a difference in the dimensionality of the training parameters of about 10 or even more. Does this justify this small difference in kind of performance? Would this justify using like this more complex or more elaborate training?
So, I mean, you see that the difference is quite small between different models, especially when you use higher amount of training data. Of course, not always you can have all this training data, so it seems that these more complex models are kind of getting better understanding of what the underlying patterns. If we look at the pixel-wise segmentation versus the half segmentation, the difference of training, so when you use less training data will be a full disaster. When you will use more training data, it will get slowly very near to the half segmentation approaches. So this one is here in ultrasound, it's, there. So 2D ultrasound semantic is the pixel-wise. So you see you have around 0.5 overlap coefficients. When you go to 3D, 2.5D and 3D even decreases more. And then half, it's more or less always the same, it's 85, right? So yeah. So this was the question, right?
Yeah, and a little bit kind of, is there a payoff between the quality that you reach and the training? Like
the training is more or less the same time, I would say.
Because for an expert, I don't know how this is used at the end, but does it make a difference for someone if someone sees such a image marked with a classifier which has 0.85 and 0.84?
This one, I mean, I think that the localization is important. The fine-grained classification is important just for the purpose of comparing with other methods and saying we are better. Of course, the more quality, the better, but in general, since it does not cost much, it's the difference between, so here it's even in 2D, so that model is cheap to build at all, completely cheap. Those that are in 3D, maybe you need 9-10 gigabyte during training of graphic card, video RAM, but during testing we tested always with a 4 gigabyte graphic card and NVIDIA GTX, I think 960, 970, I don't know. But trained on a Titanix, or 3 Titanics. because in parallel. Yeah, so I will go for the more complex one. Questions? More questions? Yeah.
So if I got it correctly at some slide before, you said that
Like
Euclidean distance between the
feature
hidden layer activations indicates semantic similarity or something.
Let's see if we find a nice slide. Well, kind of, yeah. So this one, so the feature are taken from here, right? So these 128 dimensional features, and we use Euclidean dimension, Euclidean distance to find neighbors. So when we go in feature space in 128 dimension, we do fast nearest neighbor, k nearest neighbor retrieval with Flan, which is a library that does that.
So can you comment on y squared distance and whether you have any intuition in what scenarios this might fail? For example, if you use KNN, I might imagine that if you go up to something like a 4,000 dimensional representation that it fails. Do you have any intuition there, or did you do some experiments?
It's k nearest neighbor, right? It's not k means in this sense. So it's so AlexNet is one of the most, let's say, seminal work with the convolutional neural network showed that it's possible to do image retrieval from large databases using Euclidean distances between feature descriptor of is 4096 dimensional feature descriptor. And this you could see also because if you embed all your training set in 3 dimensions, so you reduce from 128 with an embedding method like TSNAE, I think, to 3 dimensions, then you would see your images appearing based on their image content. So the one that, for example, a tree against a blue background will be very close to other trees next to a blue background. That will be directly next to trees appearing after, so on a cloudy background. And then fields, and then, because things will kind of cluster together in a way that their semantic content will be preserved. So in this sense, we wanted to, for example, the lower part of the midbrain, that it always falls near to other lower parts of midbrain. This is what the thing that we try to do. Indeed, we also tried to limit our shift invariance, because the more shift invariance, the more we are damaged. So because our votes are displacements, so we allow a minimal shift invariance through one pooling layer, just to be sure that our sampling grid does not need to be too fine.
So did you try any other distance metrics?
I am trying currently a fully convolutional way of doing it. And so doing segmentation, not of these, but heart segmentation, like left ventricle, in ultrasound still, which is has less dropout region, and they use a network that is very similar to UNet. It was presented at MICAI last year. It's a conference about medical image pattern. No, it's medical computer-aided intervention, medical imaging computer-aided intervention, true. And it's basically a U-shaped network that does convolution, pooling, convolution, pooling, convolution, pooling, then reduces the image very small after all this pooling, and then does depooling, convolution, depooling, convolution, depooling, convolution, arriving up again to the original size, and outputting a pixel-wise classification, let's say, kind of, but this kind of preserves also structure. This is very interesting, it's extremely fast, and I've done it on volumes. The original paper is in 2D, and I would like to put on top some shape constraints that should be explicitly modeled by the network but still learned. And this is kind of challenging because I started 3 days ago. But it works, tried it, it works.
Okay, thanks.
Yeah. More questions? There was him. Yeah.
So I have a question. Could you do this, like votes prediction not by using nearest neighbors, for example, but obtaining them directly from a CNN?
Yes, there are two papers, one about head pose estimation and the head landmark localization, BMVC 2014, and Mikai 2015 about cell localization in scenario like microscopy, where they do regression. So what they do is they have a fixed number of voters, which I don't, because it's like these voters can be so k and n, but they are k, but you can threshold them on the distance, and you will always output votes that are like coming from training, so they are reasonable. While they predict, for example, 20x, 20y, 20z, so three coordinates, 20 of them, and these are always 20. But regression can behave very nervous, in the sense that these outputs can oscillate arbitrarily, given also the complexity of the model, in the moment that you give in data that was never seen before. It's kind of a bit of unpredictability. This is just our idea that comes from previous works, but of course also the regression models are nice. Additionally, here we can attach whatever we want, meaning segmentation patches. We can change the size of the segmentation patches. We could even attach diagnostic information. Together with this vote, I could say healthy. And give the segmentation and say healthy or not healthy, depending on the application. So it allows for, I would say, more flexibility, and it proved to be fairly reliable.
Thank you.
Yeah, welcome. Yeah.
One more short question.
Yeah.
How long did you train for?
So the models in 2D take a few hours. The models with limited training data in 3D will take 1 day. The most complex model with the most training data that you have on a Titan X will take up to 1 week something. So we needed to use 1 Tesla, K40 and 2 Titan X to complete the experiments in a month. Yeah, 20 days I would say. Because each network is trained for all the cases, so it's really, I think 100 something trainings. Okay.
More questions? All right.
Okay, thanks a lot.
Thank you. Feel free to take some time to network, talk, meet each other.
It's okay. No, in realtà non l'abbiamo usati completamente. Sì, volendo sì. Cioè, dei modelli sono falliti e li abbiamo distanziati. So, in English, yeah. So, 6 random generations. Quindi quelli lì li abbiamo trascurati perché se l'avessimo fatto ci avremmo messo 6 mesi a farlo, però sono tanti.
La seconda è per il fatto della necessità di avere delle data. Ci sono lavori che utilizzano evolutionary algorithm, magari senza le task di qualcosa di task. Non ha la coordinata.
Si potrebbe fare, però su segmentazione è difficile, perché praticamente ci vuole proprio essere precisi e tracciare. Cioè, cose in robotica potrei immaginarmelo fare tipo con forza. Cioè lo fai e sbagli, lo fai e sbagli, fino a quando poi non serve. Però su questo qui non lo so, non credo. Ci sono dei lavori di usare il Computational Network per fare crowd annotation. Ed è un lavoro del mio collega, però non l'ho ancora letto perché l'ha pubblicato tipo ieri. Sì. Però per crowd annotation quello sì. Questo genere di cose ci vuole manual sales. Come mai siete di qua, lavorate qua? Ci sono un sacco di italiani. No, ma dico, vivete qua? Ci conoscete? Ah, ok. 2 settimane. No, io 3, io 4 anni. So, questions? Oh, more question, you? Let's do it in English. If you want, I'll answer. Okay. Yes.
So, the images, it seems realistic because you have segmentation and allocation of the
Yes.
nuclei.
Yes. So I have.
That will allow you then to volumetrics.
I do volumetric. This all is all volumetric. So even when we classify in 2D, then when we project the stuff or when we do the segmentation, we obtain as always a 3D full segmentation. Now I'm porting everything in Python and soon will be on GitHub. I'm really sorry that I could not put before the